All right, today we're diving into the invisible dangers of self-driving cars. And we're not talking about broken parts. We're talking about the code working exactly the way it's supposed to.
It sounds like a trick question, doesn't it? I mean, for decades, car safety has been all about preventing failures. You know, a brake line snapping, a sensor going haywire. But with self-driving cars, the biggest danger isn't what breaks, it's what works perfectly.
Think about it. The problem is the car's perception system working flawlessly but still misinterpreting a weird shadow on the road. Or its navigation, also working perfectly, but getting totally confused by streetlights reflecting on wet pavement. This is a whole new breed of safety problem.
So to tackle this, engineers have two different playbooks. The old one, functional safety, is for fixing things that break. Simple enough. But the new one, this thing called SOTIF, that stands for safety of the intended functionality, is totally different. It assumes every single part is working perfectly, and then asks, okay, what are the limits of that perfection? One is about preventing failure, the other is about understanding limitation, and that's the key.
So how on earth do you find dangers that only show up when the system is working exactly as it should? Well, you have to become a detective. SOTF is basically an investigative process, a playbook for hunting down these invisible risks.
The investigation kicks off by mapping the entire world of driving into 4 zones. First, you've got your known safe stuff, everyday driving, no problem. Then, known unsafe, situations we've already found that are dangerous. But the real target, the one that keeps engineers up at night, is Area 3, the unknown unsafe. This is the huge, uncharted territory of scenarios we haven't even dreamed of yet.
And that's the whole mission. The entire point of this safety investigation is to drag those dangers out of that unknown, unsafe world and bring them into the light. You explore it, you find the risks, and you neutralize them, turning that scary, uncharted territory into known safe territory, one weird scenario at a time.
And here's how that process actually works step by step. Engineers are constantly exploring the unknown, hunting for new hazards. Once a hazard is found, bam, it's identified and becomes known unsafe. Then they engineer a fix and test it like crazy. Finally, after they prove the fix works, that once dangerous scenario gets to move into the known safe zone. It's just this relentless cycle: discover, mitigate, verify, repeat.
Okay, but this brings up a huge question, right? If you're hunting for a potentially infinite number of unknown risks, when do you ever know you're done? How do you prove the car is actually safe enough to let loose on our roads? Well, first, you need what's called an acceptance criterion. And get this isn't some technical spec. It's more like a social and ethical promise. It's the big, high-level goal, like saying the system must not cause a fatal injury in any situation you could reasonably see happening.
But you know, a promise is not proof. For that, you need validation targets. These are the cold, hard, measurable pieces of evidence that back up that big promise. So if the promise is be safer than a human, the validation target might be something insane like, okay, we have to drive 1 billion kilometers in a simulation with 0 fatal accidents to prove.
So let's put them side by side to make it super clear. Acceptance criteria are the ultimate goal. That's the what. Validation targets are the practical proof. That's the how. One is basically a social agreement, and the other is pure engineering evidence. You absolutely cannot build a credible safety case without having both.
Now that we've got our standard of proof, how do the engineers actually find the evidence? Well, they don't sit around and wait for accidents to happen. They go on the attack. They actively create the worst possible nightmare scenarios for the car.
The secret to this whole investigation is finding what are called triggering conditions. And these aren't just single events. They're a combination of things, a perfect storm of factors that pushes the system right past its limits and causes it to do something unsafe.
And some of these examples are wild. We're talking about a sudden blast of sun glare as you exit a tunnel, completely blinding a camera, or heavy rain that causes a LiDAR sensor's laser beams to scatter and create phantom objects that aren't really there. It could even be something as simple as a truck carrying long pipes that stick out, totally confusing the car's idea of how big that truck actually is. These are the clues the detectives are searching for.
To make this hunt systematic, they don't just guess. They use a risk formula. But don't worry, this isn't about complex math. It's really just a way of thinking. It helps them break down a huge, scary problem like, is the car safe, into smaller, manageable questions they can actually answer with data.
So, the first piece of this puzzle is measuring how often the car does something unexpected. They call this the rate of hazardous behavior. Think of it like a detective counting clues at a crime scene.
How often does the car do something potentially dangerous, like a phantom braking event? The goal, obviously, is to get that count as close to 0 as possible.
But here's the thing. A hazardous behavior isn't always an accident. A phantom brake on a totally empty road is startling, sure, but that same exact event on a packed highway with a semi-truck right on your tail, that's catastrophic. That's the second variable, exposure. It helps engineers prioritize what to fix first. A rare bug that only happens in high-risk situations is way more important than a common bug in a low-risk one.
Now, even with all this insane testing, you can't find every single unknown risk. It's just not possible. So the most critical safety feature isn't about handling every situation perfectly. It's about the system knowing what it can handle and acting accordingly.
This concept is called the Operational Design Domain, or ODD, and the best way to think of it is as the car's official jurisdiction. It's a very specific list of conditions, like it's designed for highway driving in clear weather below 70 miles per hour. That's where the system is guaranteed to be safe. You go outside of that jurisdiction, all bets are off.
Which, of course, leads to the obvious question. What does the car do when it's about to leave its approved jurisdiction? Or what if a driver tries to turn it on when they're not supposed to?
Well, there are two main defense mechanisms. The first is called non-engageability. It's simple. If the conditions aren't right, say you're in a snowstorm, the system just won't turn on, period. The second is a safe exit. As the car gets near the edge of its ODD, like the end of a highway, it gives the driver plenty of warning to take back control.
And what happens if the driver is distracted, or maybe even asleep, and doesn't respond? The car has one last failsafe. It performs what's called a minimum risk maneuver. It won't just shut off. It'll safely slow itself down, stay in its lane, and turn on the hazard lights, doing everything it can to minimize the danger.
So when you boil it all down, safety in these cars isn't a feature you can just install, or a piece of code you write one time. It's a continuous, never-ending investigation. It's a constant detective story where the goal is to find the next invisible threat before it finds us.
The engineering process is absolutely incredible. But after billions of simulated miles and mountains of data, it all comes down to a question that engineering alone can't answer. At what point does all that proof finally become trust?